Crazy thing is that you probably already know Kirchhoff, or we should really say Kirchhoff's, first and second laws without realizing. But it's still useful to think about these laws when considering electrical circuits, as they can help us solve some complicated problems. Kirchhoff's first law is this: the total current flowing into a node or junction is equal to the total current out. You know this is true from when you learned about basic parallel circuits, no doubt. When 3 or more wires meet, there will be current flowing in and out. If we know which way the current is going in each wire, we can just equate the currents in and currents out. If we know which way the current is going in each wire, we can just equate the currents in and currents out. So in this case, I1 equals I2 plus I3. So if I1 is 5 amps and I2 is 1 amp, that must mean I3 equals 4 amps. You also might have to take a guess as to which way current flows into and out of junctions in order to use the first law, but that's okay. If you got it wrong, you'll just end up with a negative current for one of the eyes, just showing that it's going in the opposite direction to what you thought. Kirchhoff's second law is to do with voltage. In any complete loop, the sum of PD rises, or EMFs, must equal the sum of PD drops. Now the wording of this can be a bit confusing, so let's think about the simplest circuit we can make. With just a 6-volt battery or cell, yes, I conflate the two, put an angry comment below if it makes you feel any better, even though it doesn't make any difference to the circuit, and a resistor. We have a closed loop. What's the total PD rise or EMF? Well, it's the 6 volts supplied by the battery. Where's the only place where potential is dropping, or in other words, where PD is being used? In the resistor, of course. If the total EMF, we can use the symbol epsilon, is 6 volts, that's just voltage supplied, then the PD across the resistor must also be 6 volts. Let's get another resistor in series. The PD across the first one, let's say it's 4 volts, so what is it for the second? Well, it has to be 2 volts, doesn't it? 6 volts EMF, PD rise, so there must be another 2 volt drop somewhere, 2 volts being used, so that must be in the second resistor. You probably knew the answer already, didn't you? Great! Then you used Kirchhoff's second law without even knowing it. Next, let's add another 6 volt battery in series and say that the PD across the first resistor is 5 volts, say. What's it going to be for the second resistor now? Well, the total PD rise, or EMF, is 12 volts, 6 plus 6. So the second resistor must be taking up 7 volts of that 12 volts. If batteries or cells are facing in opposite directions, then one must be positive and the other negative. So let's say we have 10 volt and 6 volt batteries facing each other. We still find the sum of their EMFs, but one of them is negative. So the total EMF is 4 volts. So that must also be the PD across the resistor. Okay, so fairly easy stuff so far, but it's when we start thinking about circuits with junctions that things start to ramp up. Here's a simple parallel circuit. Now you probably know that the PD across each resistor is going to be 6 volts, but let's think about the whole closed loop part of the second law. You ever see those puzzles which are like, how many triangles can you see? It's kind of similar. How many loops with an EMF can you see here? Hopefully you said 2. Here's one and here's the other. And we can treat them separately when thinking about the second law. Now you might think, okay, but how is that helpful? It's actually when we have more complex circuits that we have to use Kirchhoff's second law. How many loops with EMFs can you see? The answer is 3. 1, 2, and 3. Is there a loop that we can figure anything out for? Yes. Loop 1 only has one EMF and one resistor, so the resistor must have 6 volts, regardless of whatever else is going on. Does that help us figure anything else out? Yes, look at loop 2. The EMF is 10 volts, and we know what the PD across one of the resistors is, so that means the PD across the other must be 4 volts. We've got everything now, but why not? Let's have a look at loop 3 as well. The batteries are opposing each other, so the total EMF in this loop is 10 minus 6, that's 4 volts. And there's only one resistor that can take up that PD, so look at that, it all checks out. If there isn't an obvious PD you can figure out straight away, you're probably going to have to use the first law in conjunction with the second law to produce simultaneous equations to solve, but that's more of a degree level deal. Hopefully you know that if you have identical batteries in parallel, then the total EMF is just going to be the same as one of those batteries. But sometimes people ask, what happens if we have batteries with different EMFs in parallel, with no resistance in between? Does Kirchhoff's second law help us then? The answer is no. One would discharge into the other, but then internal resistance comes into play and it all gets too complicated. And you know, there's the whole blowing up thing that will probably happen before you even get a chance to worry about that, to be honest. So I hope you found that helpful. Leave a like and a comment if you did, and don't forget to check out my other electricity videos and videos covering everything you need to know for each exam paper in like an hour each. See you next time.